Cloud computing. Unit 1. Redistributed systems are computer systems that consist of multiple independent computers that communicate and coordinate with each other to achieve a common goal. The goal of a distributed system is to provide users with a transparent, cohesive, and reliable computing environment. Some examples of distributed systems include cloud computing platforms, peer-to-peer file sharing networks, and distributed databases. Distributed systems are designed to handle large amounts of data, provide high scalability, and fault tolerance. In a distributed system, data and processing are distributed across multiple computers, also known as nodes, that are connected via a network. Each node in a distributed system can perform its own computations and communicate with other nodes to exchange data and coordinate activities. The main advantages of distributed systems include scalability. Distributed systems can handle large amounts of data and can be easily scaled up or down depending on the needs of the application. High availability. By distributing data and processing across multiple nodes, distributed systems can provide high availability and fault tolerance. Cost-effectiveness. Distributed systems can be more cost-effective than traditional centralized systems since they allow for the use of inexpensive hardware and the ability to use resources on demand. However, distributed systems also present several challenges such as coordination and synchronization. Distributed systems need to synchronize their activities to achieve a common goal, which can be challenging due to network latency, communication failures, and different clock speeds. Security. Distributed systems need to be designed with security in mind to protect against attacks and data breaches. Data consistency. Ensuring data consistency in a distributed system can be challenging, especially in the face of network failures or node crashes. Overall, the design and implementation of distributed systems are complex tasks that require careful consideration of many factors such as communication protocols, network topology, data partitioning, and fault tolerance mechanisms. Redistributed systems can take various forms, including grid computing, which is a type of distributed computing that allows users to access computational resources from multiple remote locations. Here are some other variants of distributed systems. Cloud computing. Cloud computing is a type of distributed system that allows users to access computing resources such as storage, processing power, and applications over the Internet. Cloud computing services are provided by third-party providers and can be accessed on demand, providing a highly scalable and cost-effective computing environment. Peer-to-peer, P2P systems. P2P systems are a type of distributed system where each node is both a client and a server, with no central authority controlling the system. P2P systems are commonly used for file sharing, content distribution, and communication applications. Cluster computing. Cluster computing is a type of distributed system that consists of a group of interconnected computers that work together to perform a task. Cluster computing is often used for high-performance computing applications such as scientific simulations and data analysis. Mobile computing. Mobile computing is a type of distributed system that allows mobile devices to communicate and exchange data with each other and with other systems. Mobile computing is used for a wide range of applications, including location-based services, social networking, and mobile commerce. Edge computing. Edge computing is a type of distributed system that processes data near the edge of the network, rather than sending it to a central server. Edge computing can provide lower latency and reduce network bandwidth usage, making it useful for applications such as the Internet of Things, IoT, and real-time analytics. Overall, these variants of distributed systems reflect the diversity of applications and requirements that such systems can support, from scientific computing to mobile and IoT applications. Each variant has its own unique characteristics and challenges, and the choice of which variant to use depends on the specific needs of the application or system being developed. Cloud computing is a model of delivering on-demand computing resources over the Internet. It allows users to access scalable and flexible computing resources, such as servers, storage, applications, and services, without having to invest in and maintain their own physical infrastructure. The cloud computing model is based on the principle of sharing computing resources, which allows users to pay only for the resources they use. There are three main service models in cloud computing. Infrastructure as a service, IaaS. IaaS provides users with virtualized computing resources such as servers, storage, and networking, which can be provisioned and managed on demand. This allows users to have complete control over the underlying infrastructure and to build and deploy their own applications. Platform as a service, PaaS. PaaS provides a platform for users to develop, run, and manage their own applications without having to worry about the underlying infrastructure. PaaS typically includes a set of development tools, middleware, and services to help users build and deploy applications. Software as a service, SaaS. SaaS provides access to applications and software over the Internet, eliminating the need for users to install and maintain the software on their own devices. SaaS applications are typically accessed through a web browser or mobile app and are managed by the provider. Cloud computing has many benefits, including scalability. Cloud computing allows users to quickly and easily scale their computing resources up or down based on their needs. Cost effectiveness. Users only pay for the resources they use, which makes cloud computing more cost-effective than traditional on-premises computing. Accessibility. Cloud computing allows users to access their computing resources from anywhere with an internet connection. Flexibility. Cloud computing allows users to experiment with new technologies and ideas without having to commit to long-term investments in infrastructure. However, there are also some challenges and concerns with cloud computing, including security and privacy, vendor lock-in, and dependency on internet connectivity. Overall, cloud computing has become an important and widely adopted model of computing, providing organizations of all sizes with the ability to quickly and easily access and use computing resources without having to invest in and manage their own physical infrastructure. Cluster computing is a type of distributed computing system that consists of a group of interconnected computers, or nodes, that work together to perform a task. In a cluster computing environment, the nodes are typically physically located in the same data center or on the same local network. Cluster computing can be used for a variety of applications, such as scientific simulations, data analysis, and high-performance computing. Cluster computing can be divided into two main categories: high-availability clusters and high-performance clusters. High-availability clusters. High-availability clusters are designed to provide continuous availability of applications or services. In this type of cluster, multiple nodes are used to provide redundancy and failover capabilities. If one node fails, the application or service can be automatically migrated to another node, ensuring that the service remains available. High-performance clusters. High-performance clusters are designed to provide maximum computing power for demanding applications. In this type of cluster, nodes work together to perform large-scale simulations, data analysis, or other computationally intensive tasks. High-performance clusters typically use specialized hardware, such as graphics processing units, GPUs, or field programmable gate arrays, FPGAs, to perform tasks in parallel and achieve high levels of performance. Cluster computing provides several benefits, including scalability. Cluster computing allows users to scale their computing resources up or down based on their needs. Fault tolerance. Cluster computing provides redundancy and failover capabilities, which helps ensure that applications or services remain available even if one node fails. Performance. Cluster computing can provide high levels of computing power and performance, making it ideal for demanding applications. Cost effectiveness. Cluster computing can be more cost-effective than building a single, high-end server, since it allows users to use commodity hardware and scale resources as needed. Overall, cluster computing is a powerful and flexible computing model that can be used to solve a wide range of computing problems, from scientific simulations to large-scale data analysis. V-grid computing is a type of distributed computing system that allows resources such as computers, storage, and applications to be shared and coordinated over a wide geographic area. In grid computing, resources are typically owned and managed by different organizations or individuals, and they are accessed and shared in a cooperative and coordinated way. V-grid computing is designed to enable large-scale, data-intensive applications that cannot be run on a single computer or even a single cluster of computers. It can provide users with access to computing resources that they may not have access to locally, and it can enable collaboration and resource sharing among organizations and individuals around the world. Grid computing can be divided into two main categories: compute grids and data grids. Compute grids. Compute grids are designed to provide access to computing resources, such as processors, memory, and storage, that can be used to run large-scale computations. Compute grids typically rely on a middleware layer to manage the distribution of workloads across the grid and to ensure that jobs are executed correctly. Data grids. Data grids are designed to provide access to distributed data resources, such as files, databases, and data streams. Data grids typically rely on a middleware layer to manage the distribution of data across the grid and to ensure that data is accessible and consistent. V-grid computing can be viewed from different perspectives, each emphasizing different components and aspects of the system. Here are the three main views of grid computing. Functional view. The functional view of grid computing focuses on the different functions and services that make up the grid system. These functions can include resource discovery, job submission and management, security, data management, and user interfaces. The functional view describes how these functions work together to provide users with access to distributed resources and to enable collaboration and resource sharing. Physical view. The physical view of grid computing focuses on the hardware and networking infrastructure that supports the system. This view describes the different types of resources that can be included in the grid, such as clusters, supercomputers, storage systems, and networks. It also describes the different types of networking technologies that are used to connect these resources and to enable them to work together. Service view. The service view of grid computing focuses on the different types of services that can be provided by the grid system, such as compute services, data services, and application services. It describes how these services are created, managed, and made available to users, and how they can be used to support different types of applications and workflows. V-grid computing offers several benefits to organizations and individuals, but it also faces a number of key issues and challenges. Here are some of the key issues and benefits of grid computing. Key issues. Heterogeneity. Grid computing involves the integration of many different types of hardware and software, which can create challenges in terms of interoperability and compatibility. Security. Grid computing requires the sharing of resources and data among different organizations and individuals, which can create security risks and challenges. Scalability. Grid computing must be able to scale up to handle large-scale, data-intensive applications, which can create challenges in terms of performance and efficiency. Management. Grid computing requires the management and coordination of many different resources and applications, which can be complex and difficult to manage. Benefits. Resource sharing. Grid computing enables organizations and individuals to share computing resources and collaborate on projects, which can reduce costs and improve efficiency. Scalability. Grid computing allows users to scale their computing resources up or down based on their needs, which can improve performance and efficiency. Access to resources. Grid computing provides users with access to computing resources that they may not have access to locally, which can enable them to perform large-scale computations and data analysis. Flexibility. Grid computing can be used for a wide range of applications, from scientific simulations to data analysis to business applications. Collaboration. Grid computing enables organizations and individuals to collaborate on projects and share resources, which can facilitate innovation and discovery. Overall, while grid computing faces some key issues and challenges, it offers many benefits to organizations and individuals, including resource sharing, scalability, access to resources, flexibility, and collaboration. As such, it continues to be an important computing model for large-scale, data-intensive applications and for enabling resource sharing and collaboration among organizations and individuals around the world. There are several types of grid computing, each with its own characteristics and applications. Here are some of the most common types of grid computing. Computational grid. A computational grid is used for high-performance computing, allowing users to access computing resources such as clusters, supercomputers, and other high-performance systems. This type of grid is commonly used for scientific simulations, data analysis, and other applications that require significant computational power. Data grid. A data grid is used for managing and sharing large volumes of data across different organizations and systems. This type of grid can be used for applications such as scientific data management, digital libraries, and other data-intensive applications. Collaborative grid. A collaborative grid is used for supporting collaboration among individuals and organizations, allowing users to share resources, data, and applications. This type of grid is commonly used for projects that involve distributed teams or that require remote collaboration and resource sharing. Knowledge grid. A knowledge grid is used for managing and sharing knowledge resources, including data, information, and expertise. This type of grid is commonly used for applications such as scientific research, e-learning, and other knowledge-intensive applications. Service grid. A service grid is used for providing access to services and applications, allowing users to access and use different services and applications over a network. This type of grid is commonly used for applications such as e-commerce, e-government, and other service-oriented applications. Each type of grid computing has its own set of characteristics, applications, and challenges, and can be used to support different types of computing and collaboration needs. By understanding the different types of grid computing, organizations and individuals can better understand how to leverage this computing model to meet their specific needs and requirements. Grid computing topologies refer to the way in which the nodes or resources in a grid are organized and connected to each other. There are several types of topologies that can be used in a grid computing system, each with its own advantages and disadvantages. Here are some common topologies used in grid computing. Cluster topology. In a cluster topology, multiple nodes are grouped together to form a cluster, with each node connected to a shared storage and network. Each node in the cluster can execute its own tasks and share resources such as memory and computing power with other nodes in the cluster. This topology is useful for applications that require high performance and low latency, such as scientific simulations and data analysis. Tree topology. In a tree topology, nodes are arranged in a hierarchical tree structure, where child nodes can submit their tasks to parent nodes. This topology is useful for applications that require high scalability and load balancing, such as web services. Mesh topology. In a mesh topology, nodes are connected to each other in a mesh-like network, with each node able to communicate directly with any other node in the network. This topology is useful for applications that require high fault tolerance and redundancy, as each node can act as a backup for other nodes in case of failure. Hybrid topology. A hybrid topology combines different topologies to achieve specific goals. For example, a hybrid topology may combine a cluster and tree topology to provide both high performance and scalability. The choice of topology depends on the specific requirements of the application, as well as the resources and infrastructure available. By choosing the appropriate topology, grid computing systems can maximize the efficiency and effectiveness of resource sharing and job execution, ultimately leading to better performance and productivity. Grid computing components refer to the different software and hardware components that make up a grid computing system. These components work together to provide the necessary functionality for the system. Here are some common components of a grid computing system. Resource managers. Resource managers are responsible for managing the resources available in the grid system, such as storage, computing power, and network bandwidth. These resources can be distributed across multiple locations, and the resource manager must be able to identify and allocate the resources to the appropriate tasks. Grid middleware. Grid middleware provides the necessary software infrastructure to manage the grid computing system. This includes software components that handle task distribution, resource management, and job scheduling. Grid security infrastructure. Grid security infrastructure provides the necessary security measures to secure the grid system. This includes authentication and authorization mechanisms, as well as encryption and secure communication protocols. Grid applications. Grid applications are the applications that run on the grid computing system. These applications may be customized to take advantage of the distributed computing environment of the grid system. Grid services. Grid services provide access to the grid computing system. These services may include job submission and monitoring, file transfer, and data management. Grid fabric. Grid fabric refers to the underlying physical infrastructure that supports the grid computing system. This includes the hardware components such as servers, storage devices, and network switches. Overall, these components work together to provide the necessary infrastructure for grid computing. By combining the resources of multiple computers and networks, grid computing systems can provide high-performance computing capabilities for complex and data-intensive applications. Grid computing systems can be organized into several layers, each of which performs a different set of functions. Here are some common layers in a grid computing system. Fabric layer. The fabric layer is the lowest layer in a grid computing system, which comprises the physical infrastructure of the system, such as the network connections and the computing hardware. Resource layer. The resource layer manages the resources of the system, such as processing power, memory, and storage. This layer is responsible for identifying available resources, allocating them to jobs, and monitoring their usage. Collective layer. The collective layer is responsible for managing a group of resources as a single entity, which can be used to perform complex computations. This layer can be used for tasks such as data analysis, simulations, and modeling. Application layer. The application layer provides the interface between the user and the grid computing system. This layer includes the applications that run on the grid, as well as the tools and services that are used to manage the grid resources. Fabric management layer. The fabric management layer is responsible for managing the physical infrastructure of the grid computing system, including tasks such as network configuration, hardware maintenance, and security. Grid management layer. The grid management layer is responsible for managing the grid computing system as a whole, including tasks such as job scheduling, resource allocation, and monitoring. Each layer in the grid computing system performs a specific set of functions, which work together to provide a powerful and flexible computing platform. By dividing the system into these layers, it is easier to manage the complexity of the system and to develop and deploy new applications on the grid. Grid computing standards are a set of guidelines and protocols that define the interoperability and compatibility of grid computing systems. They ensure that grid components and applications from different vendors and platforms can work together in a seamless and efficient manner. Here are some of the commonly used grid computing standards. Open Grid Services Architecture. OGSA is a standard that defines the services and interfaces required for a grid computing system. It is based on web services technologies such as Simple Object Access Protocol, SOAP, and Web Services Description Language, WSDL. Open Grid Services Infrastructure. OGSI is a standard that specifies how to implement OGSA services and interfaces in a grid computing system. It defines the programming model and components required to build the grid service. Web Services Resource Framework, WSRF. WSRF is a standard that defines how to create and access stateful resources in a web services environment. It provides a way to manage long-running operations, such as computations and simulations, in a grid computing system. Grid FTP. Grid FTP is a protocol that provides high-performance file transfer capabilities for grid computing systems. It is based on the Standard File Transfer Protocol, FTP, but includes additional features such as parallelism, reliability, and security. Network Common Data Form. NetCDF. NetCDF is a standard data format for storing and sharing scientific data in a grid computing environment. It is designed to support large, multidimensional datasets and can be accessed and manipulated by a variety of scientific applications. Simple API for Grid Applications. Saga is an application programming interface, API, that provides a simple and consistent way to access grid computing resources. It supports a wide range of programming languages and allows applications to be easily ported between different grid computing systems. These grid computing standards have been developed and maintained by various organizations and are widely adopted by the grid computing community. By adhering to these standards, grid computing systems can achieve interoperability and provide a common platform for sharing resources and collaborating on scientific research and development. Grid computing and cloud computing are both technologies used for distributed computing, but they have some key differences. Architecture. Grid computing is a decentralized system in which resources are distributed across multiple administrative domains, whereas cloud computing is a centralized system in which resources are provided by a single administrative domain. Scale. Grid computing is designed to handle large-scale computing tasks that require huge amounts of processing power, storage, and network bandwidth. Cloud computing is designed to handle a wide range of computing tasks, from small-scale applications to large-scale enterprise systems. Resource provisioning. In grid computing, users are responsible for finding and accessing resources and negotiating access with the resource owners. In cloud computing, resources are provisioned by a central service provider, and users pay for the resources they use on a pay-per-use basis. Workload management. Grid computing requires a complex system for managing the allocation and scheduling of computing resources across multiple administrative domains. In cloud computing, workload management is handled by the service provider, who optimizes the use of resources to ensure the best possible performance. Security. Grid computing involves the sharing of resources across multiple administrative domains, which can create security and privacy concerns. Cloud computing provides greater control over security, as the resources are centrally managed and protected by the service provider. Overall, grid computing is best suited for scientific and research applications that require massive amounts of processing power, while cloud computing is ideal for a wide range of business and consumer applications that require scalability, flexibility, and cost-effectiveness. Grid computing and cluster computing are both technologies used for distributed computing, but they have some key differences. Architecture. Grid computing is a distributed computing environment that spans multiple geographic locations, while cluster computing is a set of connected computers that work together within a single location. Resource provisioning. In grid computing, resources are owned by different organizations and are shared across different locations, while in cluster computing, all resources are owned by a single organization or entity. Workload management. In grid computing, workload management is complex, as it involves coordinating resources across multiple administrative domains. In cluster computing, workload management is simpler because all the resources are located in a single location. Scalability. Grid computing is designed to handle very large-scale computing tasks that require significant amounts of processing power, storage, and network bandwidth across multiple locations. Cluster computing is typically used for smaller-scale tasks within a single location. Cost. Grid computing can be more expensive than cluster computing, as it involves coordination across multiple locations and organizations. Cluster computing can be more cost-effective, as it involves using resources that are owned by a single organization. Overall, grid computing is best suited for large-scale computing tasks that require distributed resources across multiple locations, while cluster computing is ideal for smaller-scale tasks that require resources within a single location.